We're going to talk about bond enthalpy, the strengths of a covalent bond. The stability of a molecule is related to the strengths of the covalent bond it contains. N2 gas has a triple bond. It's very inert, hard to break. We can break these bonds and we can measure the amount of energy needed to break them, and by relating bond strength to the enthalpy change in reactions which bonds are broken. So there's really two ways to calculate a heat of formation, either using heats of formation out of the appendix or looking at another appendix or table that has bond enthalpy values. The bond enthalpy is the enthalpy change for the breaking of a bond in 1 mole of gaseous substance. So if you think about it, two atoms are bonded together. To break that bond, the system is going to have work done on it. Or if you pull apart two Tinker Toys, it's an outside force. So that means bond enthalpy is always a positive quantity. Energy is always required to break a chemical bond. Now, why are bond enthalpies talked about or exciting for us? What it says here, one usually uses bond enthalpies to estimate a change in enthalpy of a reaction only if those standard heats of formation are not readily at hand. So here is a reaction where methane gas reacts with chlorine gas. We form HCl as a product. So here's CH4, Cl2, and the reaction forms chloromethane. This would be CH4Cl plus HCl. So this is kind of nice. You can see a nice chemical model of what's going to happen. We're going to have to break a chlorine bond. That's why we have two chlorine atoms up here. We're going to have to break one of these hydrogen-carbon bonds. That's why we have a hydrogen up here. So it takes energy to break all these bonds. We go from here up to here to get a hydrogen atom. This intermediate species here, CH3 and 2Cl. And then this hydrogen is found by one of these chlorine atoms and we get HCl. The other chlorine finds this CH3 and then we get our CH3Cl. And here are these numbers plugged in, and we'll see how this calculation goes. And this tells us an endothermic reaction or an exothermic reaction by 104 kilojoules per mole. And we can see it's exothermic because we have a negative delta H. That means our products have less energy than the reactants. Energy is given off in the form of heat. So how does this work? We sum up the bond enthalpies that are broken, and then we minus that from the bond enthalpies that were formed. And so this looks an awful lot like calculating a heat of reaction using the heats of formation, but the heats of formation, it's always heats of formation of the products minus the reactants. So a little different order, but it makes sense to me, mainly when these bonds have more energy, you get an exothermic reaction. That's how I rationalize it in my mind. So here is a table of different bonds. And so I was just talking about, here it is, N2 gas. 80% of the atmosphere is N2 gas. That's kind of nice because N2 is nice and inert. And you can see it takes a lot of energy to pull apart a molecule of N2. And here's a reaction and the heat calculated using these bond energies. Here we see a typical problem using bond dissociation enthalpies. Using the table of bond dissociation energies, we're going to calculate the change in enthalpy for the following gas phase reaction. So we learned this relationship that the change in enthalpy for a reaction is equal to summing up. I'm going to just put bonds broken, and then subtracting, adding up, or the summation of all the bonds formed. Now when I look through here, I look down here and I see what I have over here, see what's going on over here, and it looks like I'm going to break a double bond, and I'm going to break this single bond. So I might come up here and write, I break a carbon-carbon double bond, and I see that's worth 614 kilojoules per mole. I see that I'm breaking a hydrogen-chlorine bond. That is worth 431. And then I might come over here and say to myself, what gets formed? I form a carbon-carbon single bond, and I form a hydrogen-carbon bond, and I form a carbon-chlorine bond. So a hydrogen-carbon bond, 413 kilojoules, a carbon-chlorine bond, 328 kilojoules, and then finally this carbon-carbon bond, which is worth 348 kilojoules. Alright, summation sign means I add these up, get 1045 over there, sum all these up, 1080. So the change in enthalpy for the reaction is going to be equal to this many kilojoules minus this many kilojoules. And you can see more enthalpy over here, so this is going to be a negative 44 kilojoules per mole. That looks like option A. So here's how we can use bond dissociation energies to calculate a change in enthalpy for a reaction. Very similar to using heats of formation. Only heats of formation, we sum up the heats of formation of the products minus summing up the heats of formation of the lattice energy and the stability of ionic compounds. So here's elemental sodium, elemental chlorine, forming sodium chloride. And here is a nice picture of sodium chloride, a nice crystalline solid where every positive sodium has a bunch of chlorines around it. Turns out positive sodium is going to have 6 negative chlorides around it. 4 in the plane and 1 behind and 1 above. We're just looking at an edge. And likewise, each chloride ion is going to have 4 sodiums around it in the plane, 1 behind it, and 1 in front of it. So it's this electrostatic attraction holding the crystal together. And that's what lattice energy is defined as. The energy required to fully separate the positive charges from the negative charges. And so how could one possibly measure such a thing? Here you see kind of a violent reaction where you have sodium metal, it's not really accurately depicted in this, and chlorine gas reacting. You can see a lot of heat given off there. So Born-Haber cycle is a cycle that relates lattice energy of an ionic compound to quantities that can be measured. So we can measure the amount of energy it takes to vaporize solid sodium into a gas. It takes that much energy. Here we can measure how much energy it takes to break apart a diatomic molecule of chlorine. And then we can measure the ionization of sodium. That's the energy required to pull an electron away and form an ion. That's why it's called ionization energy. And the energy that's given off when something accepts an electron, that's called electron affinity. So first, let's just mention lattice energy one more time. The energy required to completely separate 1 mole of an ionic compound into its gaseous ions. And there that is. That's a lot of energy. And from physics, there's this formula that says if we know the charges of our 2 ions in a constant and the distance they are apart from one another, energy associated with the electrostatic attraction is governed by Coulomb's law. We'll never do anything with this equation. It's for your information only. What we want to do is see how Hess's law plays into this. And here's the stair steps and things being done in a series of steps. And here's this thing that might be kind of hard to measure directly, lattice energy. So here we vaporize sodium metal into sodium gas. Then next we break apart Cl2 and just make it into Cl. Alright, then we have the ionization of sodium. Then we have the electron affinity of chlorine to chloride. Now we got these 2 ions that can find each other, and bam, they come together as a solid. And we can probably measure this reaction in a calorimeter and get this heat. And I said we can measure this vaporization, this bond dissociation, ionization. We can measure this. And here, then we can calculate this. Ionic compounds are stable due to their attraction between ions of unlike charge. This attraction draws the ions together, releasing energy and causing the ions to form a solid array or lattice. By accounting for all 3 energies, ionization energy, electron affinity, and lattice energy, we get a good idea of the energetics involved in such a process. Intermolecular forces, our next chapter. I abbreviate IF, intermolecular forces. It's those intermolecular forces that's going to give rise to all the physical properties that we observe. Boiling points, melting points, viscosity, solubilities, physical properties of a molecule or the molecular liquids and solids are due largely to intermolecular forces. So an intramolecular force is a covalent bond. There is the intramolecular force. Now, a force that exists between molecules we call intermolecular. And it's these intermolecular forces is the reason why real gases do not behave as ideal gas. And so from the gas chapter, you might have, that was the first time you heard of van der Waals forces. These intermolecular forces as a group are referred to as van der Waals forces. And then in the gas chapter, you probably went over all of these. Intermolecular forces are forces that exist between molecules. Chemical bonds are intermolecular forces. So there you got some repetition on that one. So the difference between states of matter is the distance between particles. Here we see a gas like chlorine gas, and you might have learned from the gas chapter that a gas is mostly empty space. And if there's a lot of empty space between here, this chlorine molecule can't really interact with this chlorine molecule. And so at a low pressure and high temperature, these things are moving around, bouncing off the walls of the container, hopefully elastically. So from physics you learn that it doesn't take any energy. Elastic collision momentum is conserved. Here we have a liquid. This looks like bromine. And now these molecules are close enough that they feel attraction. And it's that attraction which is keeping it together in the liquid phase. Particles can move around. That's why liquid flows. When we get over here, I2, now we see a solid. And we actually see a nice crystalline solid. Looks like there's some order how these are packed together. Particles are closely packed in an ordered array, locking them into a fixed position. So there's an intermolecular force, where the intermolecular forces are responsible for holding these I2 molecules right in place. There's intermolecular force holding these together in the liquid phase. Now it might look, it just probably looks like liquid on the top of the flask, but if I was going to try and breathe this flask, I'll hold it way out and waft it over. There's plenty of Br2 gas floating around above the liquid, and we'll see vapor in equilibrium with the liquid in this chapter. Because in the solid and liquid states, particles are closer together, we refer to them as the condensed phase. So here is a water droplets, and we might even decide water droplets have this shape due to an intermolecular force. And it looks like they're beating up. So this must be a nice, clean, and waxed car. My old car, they went beat up. Like water on a duck's back. What does that mean? You ever heard that expression? Rolls off. Normally you say about the person that's not bothered when other people talk trash about him or something. Or boss is mean, yells at him, or wife complains. Doesn't faze him. It's like water on a duck's back. Alright, now that we understand the idiom, what is that? What's the chemistry behind that? I guess I'm getting way ahead of myself.
I would say that the duck's back is kind of hydrophobic.
Right, it's all oily, and water and oil don't mix. Just like this car is probably waxed, and wax and oil don't mix. Right, so the state that we find the element in, or chemical sample, depends on the balance between kinetic energies of the particles and their intermolecular, that attraction between them. And I might have told you on day one of lecture that temperature is a measure of average kinetic energy, not hotness or coldness. So here's a gas, has lots of kinetic energy. We compress it and maybe remove some heat that slows them down, and once they're slowed down and don't have all that kinetic energy, their kinetic energy is less than the intermolecular forces, so the intermolecular force gets to hold them in the condensed phase of the. We remove some more heat. These will have even less kinetic energy, in which the intermolecular force is sufficient over the kinetic energy to hold these atoms or molecules in place. So here is a crystalline solid. So I like to talk about melting butter. You make some toast and you pull out that butter and it's kept in the freezer, and you're all so angry because you scrape it off and it tears up the bread, and you just can't, you let it sit out and the fat molecules get a little more kinetic energy. Then it's all soft. You put it in a glass because you made some popcorn, you microwave it, and it just pours out like liquid. Alright, if you didn't learn these in the gas chapter, you can learn them now. We're going to talk about 3 types of intermolecular forces that are known to exist between neutral molecules. We'll probably talk about a 4th intermolecular force where we have a non-neutral molecule, meaning charged ions. These intermolecular forces, as a group, are referred to as van der Waals forces. There you get that a second time. So, dipole-dipole interactions, London dispersion forces, and hydrogen bonding. So the first one we'll look at is dipole-dipole. So we have a neutral molecule, but the molecule is polar. So we imagine the positive end of one molecule is attracted to the negative end of the other. So we have acetonitrile here, and we have a nitrogen out on the end, and then a carbon, and then a CH3. Nitrogen's more electronegative than carbon. Here you can see how it's kind of a linear molecule. So with the electronegative element out here, it sucks electron density that way. That's why we have this net dipole moment here. And so this is like a frozen chunk of acetonitrile. We heat it up a little bit, and then we have a liquid, and they're moving around a little bit, and every now and then there might be some repulsive force, but the overall, from negative end to positive end, negative end to positive end, to negative end, positive, negative, and it's held in the condensed phase of a dipole interactions are effective when the molecules are very close together. That means get these as gases, they don't come to play as much. So here we have three molecules, and they're all have the same nominal molecular weight. We'll see here shortly that as molecular weight increases, so does your London dispersion force. So what we're trying to compare here is just what effect the dipole interaction has. So propane, a boiling point of 231 Kelvin. That almost sounds hot, right? Until we convert it to Celsius. 1 minus 273, negative 42 degrees Celsius. That's why sometimes when you barbecue, you don't see it so much in Wyoming. And that propane tank gets cold and gets frost. Has everybody seen that? Why does that get frost? Because of the low boiling point. So you have a lot of liquid going into the gas phase. It takes heat, takes it out of the surroundings. Must be endothermic. All right, here's dimethyl ether. Now we have an oxygen in there, so it has a bigger dipole. Here a dipole at the moment of 1.3, and now we've gone up quite a bit. Acetonitrile, dipole moment of 2.7, and now we're up to a reasonable temperature. Let's see here. 294 minus 270, 21 degrees. Well, that'll boil on the bench top, unless it's kind of cold out. Now acetonitrile, this is going to have a boiling point more close to water, perhaps. I think it might be above water. Let's see. 55 minus 270, 82 degrees. A little lower than water. So this increase in boiling point is due to the increase in the dipole force. The larger the dipole moment of the molecule, the more kinetic energy you got to impart to break those apart to put it from the liquid into the gas phase. The more polar the molecule, the higher its boiling point. So I mentioned on that previous slide that all those compounds had the same nominal molecular weight, 44 to 46. We wanted to do that to kind of hold the London dispersion force constant. Everything has a London dispersion force. It says here nonpolar gases can be liquefied. What that means is there must be some kind of force that it exists with nonpolar species. So what's going on? Electrons in an atom or molecule can create an instantaneous or momentary dipole moment. We think about maybe an electron cloud being around the nucleus of an atom, or it could be a molecule like O2 here. And if the electrons get a little lopsided, that's going to make a dipole, and that can induce a dipole on the next atom. And that's how scientists visualize a non-polar atom like argon. Now argon has like 18 electrons, 8 in its outer shell, and they can easily be lopsided or move around. So this whole thing's kind of fluid. So anything that has electrons has a London dispersion force. It's typically the weakest force, but if we have a particularly large molecule, then it can become significant. I can think of a London dispersion force as being like a penny. and maybe a dipole is a quarter. If I have a 5-gallon bucket of pennies, I'm going to have solid mass like asphalt. Asphalt's kind of a mixture, but this heavy tar. So we can kind of measure a molecule's tendency to have London dispersion force with this thing called polarizability. The tendency of an electron cloud to distort in this way is called polarizability. These forces are present in all molecules, whether they are polar or nonpolar. So you can look up polarizability values in chemical tables where physicists, physical chemists have specified two metal plates and a gas at a certain temperature, and they make an electric circuit, and they can measure like capacitance and assign a polarizability number. We don't have to do that today. All we need to realize is krypton is going to have a higher boiling point than neon because it's more polarizable. Why is it more polarizable? It has a bigger electron cloud about it. The shape of the molecule affects the strength of dispersion forces. So here is a 5-carbon chain, and here is a 5-carbon ball. It's like 4 carbons bonded to a carbon there in the middle. So these all have the same molecular weight. They have the same molecular formula. If you want to learn all about this type of stuff, we call these constitutional isomers. And we see that the straight chain hydrocarbon has a boiling point of 309.4. But this one here, where it's more like a sphere, has a lower boiling point. Long, skinny molecules like N-pentane tend to have stronger dispersion forces than short, fat ones like neopentane. This is due to an increased surface area. This looks like a good place to end for today.